Hello everyone, my name is Suresai Teja, student of Master's Case at Mahindra University. Today we are going to discuss on the topic corrosion diagnosis of rebars using uncoated rebars using piezo sensors under the guidance of me, Professor Vishalachi. Aim of the experiment is to perform corrosion diagnosis for epoxy and non-epoxy coated rebars and compare the data and check the level of corrosion using EMI technique, which is one of the structural health monitoring techniques. What and objectives is to by using EMI technique to find the variation of damages in non-epoxy coated and epoxy coated rebar, to find the healthy state and corroded state signature of non-epoxy and epoxy coated rebar using RMS technique. What is like SHM? SHM deals with the supervision of structures on a continuous basis. Supervision on the continuous basis using sensors or some electric gadgets. They are done in order to maintain the functional utility of the structure through regular monitoring, which is more or less called as a maintenance itself. This establishes the utility value or the functional value for the whole structure. Advantages of SHM: increased safety. So, how can we say that SHM is increasing safety of the structure and public life? SHM is advantages because the health can be monitored using sensors, data collection, and analysis to initiate a preventive maintenance. Further continuous monitoring and analysis of the recorded data helps to update design procedures by avoiding any flaws in the design. So it also serves as a knowledge update on the design of structures. So all these things will be bracketed under one major advantage which we call as increased safety. Second advantage is early risk. SHM can be seen as a high useful tool in preventing water and flood damages caused by failure of big reservoirs. In such cases, built-in sensors can be useful to monitor the change in water level, which can be used to detect minor leaks and major failure as well. SHM can be used as a new design tool in case of design of foundations for bridges, pavements, etc. And also, groundwater can also be monitored through SHM, which will help to predict earthquakes and to improve the structures under earthquakes. Third is the longer lifespan of the structure. Both preventive and periodic maintenance enhance the service life of the structure. Civil structural system. Continuous monitoring improves the plan for preventive and repair procedures. Most importantly, it accounts for human errors if made. SHM can also improve the existing design methods by eliminating the flaws in the design procedures. Last one is the cost efficiency. It can be helpful in effective utilization of funding towards maintenance. It can essentially avoid like unwanted maintenance of structures with good health. That is the unnecessary periodic maintenance of system already in good health and can be avoided as it improves the cost efficiency. Most importantly, it avoids shutdown operations. Right. What is corrosion? Corrosion is the gradual degradation of the metal by chemical reaction with the environment. Corrosion of steel structures reduces the life and durability of concrete. Corrosion can create volumes in a steel bar, which in turn affects the surrounding concrete, leading to cracks, delaminations, falling, etc. What is the mechanism of the corrosion? The formation of rust is influenced by the presence of oxygen, water, and iron. There are these are four criteria required to initiate corrosion: rupture of passivating film depassivation, oxygen availability, and a conductive medium between anode and cathode. Okay, now we'll see the materials required for experiment. Like 4 iron rebars, dual power DC supply up to 30 volts for accelerated corrosion, NaCl and H2SO4 solution up to 3% concentration, single stranded wires, copper rods which access cathode, PZT sensors, soldering equipment, LCR meter, two different types of epoxy. We need two different types of epoxy for good bonding of sensor with rebar and zinc primer spray coat. Okay. Why we are going with NaCl solution of 3% concentration? Salt is here. Salt is hygroscopic, meaning It absorbs water from air. This makes it possible for corrosion to occur at lower relative humidity levels. Secondly, salt increases water's ability to carry a current and speeds up the corrosion process. And why we are choosing H2SO4 solution? Here, sulfates will break into concrete. They react with calcium silicate hydrate, which is responsible for holding the concrete that is being damaged. These reactions form products like ettringite, which are expansive in nature. And these expansive products occupy empty pore space, which allow concrete to further to crack more and get exposed to atmosphere. Hence, the bar corrosion and durability of concrete is also affected due to this sulfate attack. Zinc primer spray paint is used as epoxy to protect rebar surfaces from corrosion. Mechanism is when this coat is applied, first the zinc oxides itself instead of rebar present beneath it, hence preventing corrosion. Okay. These are the images of the equipments taken. Methodology. EMI technique can be employed to monitor loosening of bones of concrete steel composite girder, monitoring corrosion in rebar, and monitoring of soil excavation. In EMI technique, a PZT patch is surface bonded or non-bonded and electrically excited by LCR meter. Upon excitation of the patch, the elastic waves generated by the patch travel radially outward in the structure and are reflected back on encountering any crack or damage. The PZT structure interaction is captured in the form of an admittance signature consisting of conductance, real part, and susceptance, imaginary part. And with the help of healthy state signatures and covered state signatures, using the RMS technique, we can determine the extent of corrosion. Here, RMS is defined as the root over the conductance of PZT patch minus the baseline value whole square to the root over baseline value whole square. Experimental setup and procedure. Here a feed 250 rebar of 16 dia is taken of, and cut into a height of 10 centimeters. As the surface of rebar is not flat, so with the help of equipment available in the mechanical workshop, the rebar surface is made flat to bond the PZT. And a small part of bar rebar is cut and made it cut into a flat surface. Specimens are is thoroughly cleaned with the help of sandpaper and acetone before bonding PZT. And after cleaning it, a very thin layer of epoxy is applied on the surface, and PZT is surface bonded and left to dry for 30 minutes by applying some weight. Then soldering is done to all the specimen. And also after the soldering, and another layer of coat is applied over the PZT for its protection in harsh environments and left it dry for 24 hours. After leaving it dry for 24 hours, in the next step, the healthy state signatures were taken using LCR meter for all the specimens. Okay, these are the healthy state signatures for reverse specimens. You can see that the PZT signatures are in the angle of 45 degrees, which indicates that no, sorry, the susceptance signatures are in the angle of 45 degrees, which shows us that the PZT is in good health. So next step is the axial corrosion of rebars. Here rebar acts as anode and copper rod acts as cathode, and the solution has a concentration of 3%. We need to perform electrolysis for accelerated corrosion under a constant voltage of 15 volts, and the supply should support up to 2 amps of current. Here ferric oxide is formed as a result of the reactions. The iron reacts with the hydroxide ions in water to form ferrous hydroxide as green rust. This again reacts with water in order to form ferric hydroxide as an end product, which is the reddish rust. Solutions used are NaCl. Here the specimen 4 is a normal rebar and whereas specimen 5 is a zinc a primer coat epoxy coated rebar. H2SO4 in similarly in H2SO4 specimen 3 is the normal rebar and specimen 1 is a zinc primer coat epoxy coated rebar. So these are immersed in one epoxy coated and one normal rebar is immersed in NaCl solution. Another normal and epoxy coated is immersed in H2SO4 solution. Okay. This is the image of auxiliary corrosion for epoxy coated and non-epoxy coated rebars in NaCl solution. Here you can see that a constant voltage of 15 volts is applied. So this is the rebar, non-epoxy coated and epoxy coated rebar dipped in H2SO4 solution. Okay. Here for NaCl solution we are taking the reading after every 1 hour. 1 hour. After every 1 hour, we will remove the specimens and left it for dry for 30 to 45 minutes. Then connected susceptor signature readings were taken with the help of LCR meter. And also after every hour, even the mass of each rebar is being calculated to see the change in the mass in the beginning and at the end of 7 hours. Similar procedure is adapted for H2SO4 as well, but the readings are taken after every 15 to 20 minutes because rebars were corroding very fast in sulfuric acid solution as it is highly acidic in nature. Okay. This is the axillary corrosion of NaCl. After every 1 hour, you can see the images of the rods like how much it got corroded. When we compare with the first hour and sixth hour, we can see a clear change in the corrosion. And also after every hour, connectance G and susceptance B, which is divided by B. These graphs were taken. As you can see, for first the non-epoxy coated specimen, the, the conductance graphs are clearly decreasing when compared with the healthy state signatures. We will see this comparison graph in the coming slides. Also, when compared with the first star, these conductance signatures are somewhat decreased in the seventh hour. Similarly for epoxy coated as well. But in epoxy coated, there is less severity when compared to non-epoxy coated because in the epoxy coated, zinc primer spray kit oxidizes itself before it oxidizing the iron. So we can see there is not much change in the epoxy coated specimens in the conductance graph. This is a comparison graph and RMSD graph for epoxy coated in NaCl. Here you can see that the blue line is a conductance signature and CD is to represent after 1 hour of reading. After 1 hour of electrolysis and series is depend on 2 hours of electrolysis. Simultaneously it goes up to series 8, which is after 7 hours of electrolysis in NaCl solution for accelerated corrosion. Here you can see the clear change in the baseline reading and after 7 hours of reading. There is a decrease in the conductance signature. So most of the thing is overlapping, but between the frequency range from 18,000 to 28 30,000, you can see a decrease in conductance. This is a RMSD for epoxy coated. Here, with the increase in the level of corrosion, the, the RMSD graph should also increase. But here, the RMSD graph is decreasing. So this change might be due to that. Indicates that we have to do this accelerated corrosion for more 2 or 3 days. Else, the concentration is less in the solutions. That is, we have to take this concentration from 3% to either 4, 5, or 6% to get a good variational change in these graphs. Okay, this is for non-epoxy coated and NaCl. Here also non-epoxy coated characteristics is decreasing in after 7 hours when compared to the first hour. So most of the characteristics signatures are overlapping with the baseline readings. Okay, this is the RMHD for non-epoxy coated. Here also it is the same reason as mentioned above. Okay. There is also not much change in mass. In epoxy coated, there is only a change of zero point 0.2, 0.31 grams, whereas in non-epoxy coated, a change of 1 gram. So as I said, it should be so the experiment should be connected for at least more 2 or 3 days to see a drastic change in mass and change in diameter as L, or you can increase the this NaCl solution and H2SO solution concentration. Okay, now this is the accelerated corrosion in H2SO4. You can see, so it is done only after every 15 minutes interval. So you can see a clear corrosion between in the first 15 minutes and after 90 minutes, the bar is corroded, and we get G and B graphs after every 15 minutes. This for non-epoxy coated. We can see we can see a clear decrease in G graphs, conductance graphs, and for epoxy coated. In epoxy coated, there is not much change in conductance graphs as the zinc primer coat protects the iron rebar, and also with the from the substance graph we can say that by seeing only PZT is in good health and is very well bordered with the rebar. Okay. This is a comparison graph of epoxy coated. As I said, zinc primer protects the iron rebar, so the baseline the reading and the after the 1.5 hour the reading, both the readings are getting overlapped, indicating that there is no much corrosion has happened, no much like significant corrosion has happened to the specimen. And here RMHC signature is minutely increasing with increasing the level of corrosion. This graph is for non-epoxy coated. In non-epoxy coated, you can see there is a clear decrease in the connected signature between series 1 and series 8. Series 1 is the blue color line, and series 8 is a brown color line. So you can see a clear decrease in the connected signature. And here also RMHD is increasing with increasing level of corrosion. Also, there is a minute change in mass in both epoxy and non-epoxy coated specimens. Results: when a constant voltage is applied in the to the rebars in NaCl solution, there is a decrease in connected signatures. Also, health of PZT can be monitored in susceptance graphs, and from the graph we can infer that PZT is in good health. The noticeable difference before and after accelerated corrosion can be seen in the comparison graph, indicating reverse damage has resulted. There is also a change in mass of rebar due to corrosion. This change is very minute. In RMHT, when one rebar corrodes over time, RMHT percentage should rise significantly. Only small variations in RMHT percentage are seen here. These are the differences. Thank, thank you.